When executives draft a strategy, assign resources, and instruct their teams, they generate momentum. However, initiating action offers no guarantee of long-term accuracy. Operational execution is subject to entropy, the natural tendency for complex work activities to drift away from strategic targets due to friction, miscommunication, and changing environmental variables. Countering this decay requires the implementation of a formal, continuous feedback loop. In management theory, this mechanism is controlling. This function monitors actual performance, compares it against established standards, and executes corrections. An organization lacking a dedicated controlling function operates as an open-loop system, making its operational drift inevitable and its long-term survival statistically improbable. Strategic planning and operational control function as the two interlocking halves of a single organizational engine. The planning phase generates specific goals, objectives, and strategies. These parameters serve as the strict mathematical targets for the entire firm. As the firm organizes its structure and leads its resources to execute the work, those activities yield tangible, measurable outcomes. This diagram illustrates how the controlling phase captures those outcomes and feeds the resulting data directly back into the planning phase to inform the next strategic iteration. This feedback cycle establishes management as a closed, self-correcting cybernetic loop. The internal architecture of the controlling function follows a rigid, three-step algorithmic process. As mapped in this diagram, the process begins by measuring actual performance, moves to comparing that performance against a standard, and concludes by taking managerial action. Step 1, measurement, is governed by the principle that managers cannot control systems they do not accurately measure. Establishing systemic telemetry requires aggregating data from diverse sources, with each method presenting specific structural trade-offs. This chart compares methods. Personal observation provides unfiltered first-hand knowledge, though subject to bias. Statistical reports offer objective data, yet ignore subjective factors. Oral reports allow fast feedback, but lack formal documentation. Written reports provide an archived record, but require more preparation time. High-fidelity measurement architectures utilize a matrix of these methods to balance the friction of data collection against the depth of the resulting intelligence. In Step 2, raw operational telemetry is compared against a baseline standard. Without this comparison, the data remains inactionable. This visualization introduces the acceptable range of variation. These mathematical parameters define how far performance can fluctuate from the standard before the system triggers an alert. Data points that breach these upper or lower limits signify a systemic anomaly requiring immediate management attention. We can apply this filter to the July sales data for Green Earth gardening supply to identify critical deviations. This table tracks the target standard against actual units sold. Vegetable plants show a critical anomaly, falling 162 units below standard. Conversely, heirloom seeds show positive deviation, surging 132 units past expectations. Deviation in either direction, whether falling short or surging unexpectedly, signals a system out of equilibrium that demands intervention. Step 3, managerial action, subjects these deviations to a rigid decision tree. This flowchart maps the logic gates a manager must navigate. If the standard is attained, the system remains baseline. Do nothing. If performance fails that gate, the manager asks, is the variance acceptable? Minor fluctuations within expected parameters pass through easily and trigger no action, conserving critical organizational resources for much more significant systemic threats. When variance is unacceptable, the manager reaches the most critical logic gate. Is the standard itself still acceptable? In the case of heirloom seeds consistently blowing past targets, the data suggests the original standard is mathematically flawed. This requires a revision of the standard. The manager must raise the difficulty to match current reality and feed that updated target back into the loop. If the standard is realistic but performance failed, the manager must identify the cause and execute a correction. Immediate corrective action serves as triage, fixing the problem at once to return the system to its expected track. Basic corrective action bypasses the surface symptom to investigate and resolve the root structural flaws that allowed the deviation to occur. Executing these decisions ensures that broken outputs are repaired, while obsolete strategic targets are ruthlessly discarded. Relying solely on correcting outputs means the organizational damage has already occurred. Advanced control architectures mitigate this by mapping feedback loops across 3 distinct temporal phases. Feed-forward control is the anticipatory layer, implemented during input to prevent errors. Concurrent control provides a real-time layer, deployed during the process phase to course-correct in motion. Feedback control is the post-hoc validation layer, capturing final variants to refine future cycles. Organizations achieve maximum effectiveness only by distributing these correction protocols across all three temporal axes simultaneously. Operating these loops requires a continuous supply of data and a clear understanding of what the baseline of excellence should be. The Management Information System, or MIS, acts as the central nervous system that translates raw data into standardized, actionable intelligence. These systems feed comprehensive measurement tools like the Balance Scorecard, which tracks organizational health across multiple functional perspectives to prevent over-indexing on financials. High-level standards are identified through benchmarking, the systematic search for the best practices used by top performers in any industry. These external benchmarks serve as the ultimate standard of excellence, forcing internal systems to evolve and meet the absolute ceiling of operational potential. When fueled by accurate information systems and pushed by rigorous external benchmarks, the cybernetic control loop drives aggressive, systematic evolution.